we will be talking about the F1TENTH Sim Racing League, which is now released as an open source competition framework for promoting reproducibility and benchmarking in the field of autonomous driving or racing in this case. So just a glimpse of what we'll be going through. First, we'll give an overview of the AutoDRIVE ecosystem as well as a generic overview of F1TENTH. Then following that, we will be talking about the competition in detail. After that, we'll be talking about how the ecosystem and the competition both come together to foster reproducibility and benchmarking. And finally, we'll open floor to questions or discussion if there are any. So let's first talk about the overview of the ecosystem. So as Dr. Mangaram already highlighted in the first talk of the day, the F1TENTH ecosystem is mainly catered around the 4 points that you see here. It's about building the F1TENTH race car that you see here as a hardware, starting from just a bare-bone Traxxas RC car chassis, all the way up to it functioning as a fully autonomous small-scale vehicle for in-lab research. This is followed by learning resources that are now catered for various level of graduate and in some cases undergraduate courses at different durations and with a different depth of academic rigor. Then, of course, there is the most exciting part of autonomous racing and competitions that, as Dr. Mangaram highlighted, is the core crux of why F1TENTH has become so popular. And then there is the research component, which basically enables the researchers from all over the world to use F1TENTH as a base platform to implement and deploy their algorithms and validate their results. More towards what we will be discussing today is the AutoDRIVE ecosystem, which is another open source effort that is led by ARMLab. And here, for example, what you see is a lot of things. So let me help you navigate through it. At the center, you see the AutoDRIVE ecosystem's architecture, where the idea is to now unify the pipeline for developing, simulating, and deploying autonomy algorithms at different scales and complexities. So you have the AutoDRIVE Dev Kit, which is a collection of software development APIs, tools, frameworks, programming languages. And as you can see, we have a support for quite a lot, even as we speak. And there are, of course, more to be added in the future as well. But what this allows is to now develop autonomy algorithms for both autonomous driving or racing, as well as smart city management or other kinds of infrastructural components that now come together to interface either with the simulator. So you can now interface the algorithms in real time with the simulator to validate them, maybe cross-validate them across different conditions of the environment or the vehicles. You can even validate them across different scales of the vehicles. And then finally, the AutoDRIVE testbed, which now unifiedly allows you to transfer those algorithms from simulation to reality, in most cases, in zero-shot transfers. So let me take a moment here to now talk about why we have written the testbed and simulator conjunctly. And that's because of the notion of digital twinning. So if you see in the top left, we have different vehicles represented as the physical counterparts that you see in the first and the third columns, and their respective digital twins, which are the second and the fourth column. So we have got small scale vehicles like the Nigel, which is an four-wheel drive, four-wheel independent steered vehicle, which is the native vehicle for AutoDRIVE. And again, the vehicle is completely open source, both the hardware and the software. Then, of course, what we'll be talking most of the time today is the F1TENTH vehicle, which is mostly targeted towards autonomous racing and like generating the excitement of autonomous racing and competition to now foster autonomous driving and learning in general. You then have the Husky robot, which is a quite famous product from ClearPath Robotics, now by Rockwell Automation. But yeah, that is a famous platform, so that is there. You have the AgileX Hunter SE, which is an Ackermann steered platform, also similarly mid-scale robot as the Husky. And then finally, in full scale, you have the Clemson Open CAV, or the Open Connected and Automated Vehicle, as well as a Razor, Polaris Razor, which now target the on-road and the off-road domains of autonomous driving. One key thing that binds all of this, as that you see here, is that these are all available physically in our lab, the ARM lab at CU ICAR. And that's the reason why we are primarily like highlighting these vehicles, because we get to work with them every day. We can calibrate the digital twins, we can run the algorithms, we can test them, we can benchmark them, and then repeat these cycles n number of times because we have access to these robots. But of course, this is also possible with other vehicles or if you see down below, environments. So talking about environments, you again have different variations in the environments ranging from small scale to full scale. As we all know, typically small scale environments are constructed in lab or within houses in some cases. And that's why you can predominantly see some synthetic materials like the boxes or vinyl stickers, or in the case of F110, air ducts being used as the material to construct these environments. In the mid scale, you have a mix of either naturalistic scenarios that you see in the forest scenario, for example, or artificial scenarios for in-lab research like the proving ground that's comprised of traffic cones. But moving to full scale, you have more higher fidelity and detailed scenarios like an off-road environment or even a downtown or a like structured city scenario. What's also interesting is to note this particular scenario that we call the CUI car Greensword, and let me try to zoom in on it. What this is an actual digital twin of one of the off-road patches in our campus that we have now replicated exactly within the simulator to carry out the virtual prototyping and then transfer algorithms from sim to real in zero shot. So that brings me to the last part of the ecosystem, that is the APIs and HMIs. I already discussed briefly about the APIs, which basically allow people from different community or different backgrounds to now get or enter into the autonomous driving domain, where, for example, not any programming language or a particular framework should be a barrier for people to enter into robotics or autonomous systems. But if you have background in any of these, you should be basically capable of developing your algorithms. That's the whole point of having a variety of APIs. And same applies to the human-machine interfaces as well, where autonomous driving is not just autonomous. You need manual interventions. You need manual driving to record data sets. You need human inputs to now, say, have active learning kinds of components. So for that, both for perception or observation as well as for control or interaction, different HMI inputs have been supported for targeting both the simulated vehicles as well as the real world vehicles. So yeah, going back to the F110 part, here is the F110 digital twin in action, where you can see, for example, the simulator supports single agent racing. It supports multi-agent racing as well, where you will see shortly two cars racing head-on with each other. What's interesting to now see is the higher fidelity of vehicle dynamics as well as sensor simulations being brought into the picture, where you are talking about these small race cars going at, say, 40 miles an hour speeds, which is basically breaking the traction limits of the tires and those kinds of effects now coming into the play. So you need very detailed simulations to make sure that your algorithms can be transferred from simulation to reality. At the same time, you also have the options of in multi-agent racing, for example, you can have races of human versus human. You can have AI versus AI, or you can have mixed races where you can compete humans against an AI opponent, which can be particularly interesting to see how autonomy is performing or being benchmarked against manual perceptions. Here, what you see is just a demonstration or depiction of how you can leverage simulations. For example, in this case, for training RL algorithms, where you have the option of parallelizing different agents or environments and then accelerating the training times to now ensure that you have iterative results and can go back and forth between the development and deployment cycles. The video hereafter will just show some cool things that we observed while the vehicles were trained using reinforcement learning algorithms to now overtake or compete against each other. But what we can do with F110 can also be similarly scaled up to different vehicles or different operational design domains. And what you see particularly here is a Polaris RZR now being simulated in off-road conditions, where, for example, the same ideology of the F110 sim racing can be applied for RZR sim racing. And this can basically make the challenge, I wouldn't say 2 times or 10 times, but maybe 100 times more complex, where your environment is not structured, your algorithms are going to be having or going through much more uncertainty than what they would in an F110 Sim Racing League. And now your objectives could be completely different. So rather than minimizing lap times, you can have completely different objectives in the autonomy pipeline. And that will basically foster a different whole new paradigm of competitions within the off-road domain. Another thing that's very important or like interesting with simulations is that you can, as I already showed you, parallelize and accelerate them, but not just on your local computes. You can put them in the cloud and leverage the power of cloud infrastructures such as NVIDIA or AWS or others to now massively parallelize them within the cloud and have the clients just connect to the cloud instance and have their interface both for API as well as display forwarding enable them to now remotely develop their algorithms and have them tested in a much standardized way. What you see here is one of the works that we had with the US Army, where we deployed massive workloads of simulations parallelly within the cloud to validate an off-road autonomy algorithm. And now the most important part for any simulation is the sim to real gap. And what this video basically shows is two different case studies, one of cooperative multi-agent reinforcement learning, and the other one is the competitive one, for which you already saw a glimpse of before. But the idea is now you train in the simulation environment and now transfer the trained policies zero shot within the real world. And what we went ahead and did here in this case was a step further. Since we are dealing with multi-agent setup here, we thought of instead of having all the agents replicated or transferred in the real world, can we now leverage just one physical agent here and have all the other virtual peers within the digital space and let them collaborate with or compete with each other via a cross connection of a true digital twinning framework. So what you see here is basically only one vehicle, both in case of F1TENTH or the Nigel, being driven in the real world, updating its states within the digital space. And now the digital agent decides of what actions are to be performed in the next time step, and those are replayed back in the real world. So that way you can actually now benchmark the simulation directly against the real world instead of having a sim-to-sim comparison, for example. I'll now ask Chinmay to give a comprehensive overview of the competition.
Thanks a lot, Tanmay. Am I audible? Okay. So let me now talk about the F1TENTH Sim Racing League in particular. So this Sim Racing League is a part of the larger F1TENTH Autonomous Grand Prix that has been around for a long time. So even like as we speak about this IROS 2024 particularly, the 21st F1TENTH Autonomous Grand Prix can be broken down into two components. One is the conventional physical racing league, which constitutes of around 20 teams, and this competition will be taking place in the upcoming days, and it will be visible to all the people who are attending IROS. So that component, exciting component, is there. And in addition to that, what we have introduced for the very first time for this IROS iteration is the first ever Sim Racing League, which got an overwhelming response of around 58 teams registering for the competition. And the format of this competition is completely virtual. You can be anywhere around the globe and you can still participate. The competition framework has been standardized and multiple people can use it, and they can develop and debug and test their algorithms, refine their algorithms, and then submit them as their entries. The competition will features a virtual F1TENTH race car as well as the racetrack for like which exactly digitally recreates the F1TENTH competition of autonomous racing. And the format that we had introduced for this very first iteration was time attack racing format, which constituted of one warm-up lap, which was not counted for in terms of the metrics used for evaluation, then followed by 10 racing laps, and then finally one cool down lap, which was again disregarded from the metrics perspective for ranking the different teams. Also, on this slide, the video that you are seeing is a summarized video of the actual deployment of the competition. These are some of the solutions that the teams actually have ended up submitting. Some of them used reactive racing algorithms, some of them used map-based algorithms, and some of them have even ended up using learning-based algorithms, which was very innovative for this kind of category. And this also gives us the opportunity to now benchmark these different categories or different methodologies or algorithms with respect to each other. as well as testing their actual transfer from simulation to reality when we talk about the physical racing league. So now let me talk a little bit about the structure or the framework of the competition that we have set up. So in terms of the logistical aspects, first of all, we have a qualification round in which the objective for every team is to complete at least 10 consecutive laps without colliding, and there is a penalty of how depending on the number of collisions you encounter, and there is also a termination criteria where if a particular team exceeds the number of collisions, they are disqualified from the competition. And all the qualified teams then move on to the competition round, where the primary objective is to now be as fast as possible, but again simultaneously being safe. So again, here as well, we have introduced a collision based penalty, but the ultimate objective here is to now make sure that you rank yourself on the leaderboard, as opposed to the qualification round where the rankings are not that significant. So in one of the previous talks, we saw the importance of how software reproducibility works. You can have dependency conflicts. You can have issues that limit you from downloading or even installing the software all the way up to building and then trying to reproduce the results. So on the similar lines, what we have also adopted is a containerization approach, where we have two different containers, one in which we run the simulator image, and that basically takes care of, first of all, running the digital twin of the race car as well as the racetrack. And then also on top of that, two additional components, which are, first of all, GUI forwarding. We need to make sure that the graphical user interface of the simulator application, as well as all the other auxiliary components, are being forwarded from the Docker image. And the second aspect here is the exposure to the API, which facilitates the data exchange between the simulator and the dev kit. The second container is that of the dev kit itself, where we have, again, two components. One is a baseline ROS2 package that we have written for all the teams as a starting point and tested as well. The other component is the team's own contributions or their own software stack for autonomous racing applications. So that constitutes the overall framework. And one of the things upon interaction with different teams, what we had observed is some teams may not have access to the exact same computational resources, or they may have different operating systems running the framework on. And such challenges, to tackle such challenges, what we came up with is additional two modes of operation. One is a distributed computing mode, where these different container images can now be spun up on different compute nodes or different computers altogether that are now just connected by a common network. And still the data exchange and the GUI forwarding is working perfectly as expected. And this way we can now distribute the computational load on different nodes or different machines altogether, thereby enhancing the capability of the real-time factor of the simulations. The other aspect is running the simulations or the dev kit in a GUI mode or a headless mode. And that also has significant effects on the computational performance, because the rendering aspects of these applications are quite heavy in most of the cases, as we can see from the graphical fidelity point of view. So in order to tackle those challenges, teams can run their or choose to run their solutions in a headless mode as well. So now let me talk about how all of this comes together and ties to the theme of this workshop, which is reproducibility and benchmarking in robotics. So first of all of these things or aspects that we have been discussing, all of them have been open sourced. Both F1TENTH as well as AutoDRIVE are massively open source efforts. We also have access to now different benchmarks and standards that could constitute things like code bases from previous competitions, or the access to the competition framework or the documentation aspects of how to use or reproduce these results in general. We have also now the capability of deploying these in the context of different research or educational activities or competitions that we are now already doing. And all of this can now be tied together with the three different components, which are software simulation, the hardware testbed and deployment, and the software development framework that is now common to both of these, meaning the simulation as well as the real world. And finally, we have the benefit of connecting with an international community, so that this does not remain a localized effort. It becomes a more distributed and collective effort from across the community. Yes, and this brings me to another important point in terms of the reproducibility and benchmarking of the results, which is the data. Currently, we all are aware of how valuable data in general is, but in terms of reproducibility or benchmarking more specifically, we need access to data sets that kind of make this happen. So at least for this specific competition, what we are kind of doing here is, first of all, recording all the incoming and outgoing data streams that the competitors are exposed to. And in addition to that, we are also recording all the additional debugging data streams that give us the information about the ground truth values, for example, or other aspects of information that are not necessarily shared with the competitors or the participants, but can be still leveraged in terms of the overall data set that we have. And here is a particular image towards the top left, which depicts a particular data frame from a single run of a single competitor. And what is now possible is we can run different competitors' images. We can run the same competitor image multiple times, and that can lead to a huge amount of data that can be then exploited for analysis and benchmarking applications. The other aspects are screen recording for visual data replay and manual analysis of the performance of different algorithms, and auxiliary metadata pertaining to the team demographics or the approach descriptions and the algorithm structuring can also be simultaneously curated alongside this main data set pertaining to the different racing benchmark and metrics. So that being said, another important aspects in terms of the data itself are visualization and analysis. So here what we have tried to create is a Foxglove layout for analyzing different race KPIs. For example, the lap counts and the lap times of each team, the collision counts and the total as well as the adjusted race time, which serve as the benchmark for metrics for ranking the different teams, as well as the best lap time. In addition to these, what we have also implemented are custom logics, which let us, for example, as an evaluator, analyze the performance of different vehicles. For example, you can see the race lap and the qualified or disqualified indicators here, which basically mark if the current lap is a race lap, or is it a cool down lap, or is it a warm-up lap. And if the collision counts or other rules are violated, then it can basically enable us to now justify if the team has qualified or it has been disqualified, and if so, at which particular instant did these events triggered, and was it a glitch, or was it an error of some sort, or was it a consistent repetition that we have observed. Other aspect here is that of vehicle KPIs itself, which could consist of the pose, twist, and acceleration values, wheel rotations, actuator feedbacks, LiDAR and camera data. All of this can now be analyzed in real time, as well as recorded for analysis at a later point in time as well. And the video that you see kind of captures all of these aspects. For example, you have the live camera feed from the vehicle. You have different indicators representing the different control actions, as well as the speed or certain parameters. You have one of the most important metric in terms of racing, which is the GG diagram, indicating the lateral and longitudinal instantaneous accelerations of the vehicle. Then you have all the different states. You have the current race log and the race event triggers, for example, which is very difficult to do in the real world, but can be now configured in simulation software to generate synthetic triggers at different instances in time to make sure that we have access to all of that data after the run. So that brings us to the end of our presentation. We have provided the set of resources that can now enable others to explore these resources or get started themselves as well. Thank you.